It's a more peaceful time for me to do this on the calculator. Okay. So, let's say that we take the radius, and the radius is the golden ratio. All right. And we try to get the circumference out of this radius, which gives us that. All right. Now, if ever I go onto the geometry pad and I create the square out of the circle using the formula by Samuel LeBoy, engineer from Puerto Rico. You have to look him up. This guy, he found a way to square the circle, and so in this way, he was also able to. I guess he was not able to uncover pi because this other pi was already uncovered by other people like Jain 108, Ari Lair, Guido Musbrugger, who's a friend of Billy Meyer. For those of you who follow the Billy Meyer case, it's very interesting. You have to check this out. And it's pretty much insightful. It gives you a whole lot of knowledge on the real. I should have written down at least a key like that in the description. But in anyways, so let's just say that that number right there is the circumference, okay? And so, of course, if that's the circumference, then the square should have a length of that right here. Notice how that it looks a whole lot like the square root of 5 right there, you know? But the length at which we're going to get is going to be exactly the square root of 5 using the golden ratio as the radius. And so let's create that circle. Okay, all right. So just on a sec, I'm just gonna remove a whole lot of that. Okay, so we're making a circle. That circle is going to be of a radius of, like we said a few moments ago, it's going to be of a radius of the golden ratio. Right now it gives the radius of 1, and it shows that the area is 3.1415927, which is the pi which we all know about and which we all live by. But I'm going to show you that this pi is not the pi we should live by. Rather, the one that you were supposed to live by is the one I'm going to show you in a few moments. So radius 1 plus the square root of 5 divided by 2, and we got our radius. And as you can see, circumference right there, again, is exactly the same as that which is shown on right here, right there. Yeah. So exactly the same. So now that we have our circle, I'm just gonna put the guides right there, and I don't need that no more. So now, just to be certain again that we know that the radius is exactly what we said it is, we're just gonna put a segment right there. Just on a second. God damn. Why does it have to be this way? Just hold on a second. I'm having issues with geometry pads sometimes. Whenever I take off the grid, all of a sudden, yeah, anything I try to connect to the bisect, it starts to slide, and I'm like, why? Why does it have to be this way? So, as we go back and we check, I'm just gonna lock these. All of these are locked except that one, and we see that the radius is exactly that. So once we're going to create that square, we're going to expect that square to have a parameter of exactly the same as the what's the name again? Parameter the same as the circumference, yeah, as a circle, you know. So we're going to take one circle right here, draw it right there. Then we're going to create another circle right here, draw it right there. And if yesterday, yeah, you remembered when I put two circles like these, that angle right there is exactly 30 degrees. Like, I mean exactly 30 degrees, you know. That's deep. I like that. So and that one right here is if you know, okay, like the Pythagorean theorem, then you would know exactly, okay, what this is. Let me show you. I'm just going to take this off right there for a moment, just so that I can show you what the triangle is all about. Yeah. Let me take this off. I don't need that. And right here we have the golden ratio. And right there we have 2 times the golden ratio. And right there we have that's deep. That's basically let me show you what this is. Yeah, if that side right there, okay, the golden ratio, the 1.618034 was 1, then the 3.23, that's 2, and like the slope itself would be the square root of 5. So if ever I was to, let's say, take the golden ratio multiplied by the square root of 5, that gives us exactly that. And that's intense. That's pretty much intense. But let's move on. Yeah, we're just gonna take off this and go back with what we've got right here. Yeah, now we've drawn a line which goes from the bottom of the first circle and goes straight to the center of the third circle, and out of this we create one circle which ends right at the edge of the third circle, bisecting the line between bisecting the point between the line and that third circle, you know. And so now what we can do is simply remove these two other circles which we don't need anymore, leaving the fourth one which we've just created. And all of this is out of one circle. Yeah. Now we have this, and from there we create the pyramid. Yeah. And so that pyramid, based on the angles which we have now, but I guess there might be a mistake, I don't know, but based on the angles which we have now, it's going to give us an angle of 51.82, 72, 92 degrees. Yeah. And let me remove that fourth circle. And if you've noticed that the fourth circle, the radius of it is 2. Surprisingly, the radius of it is 2. So now, if we look at the pyramid reveals to us a very surprising gift, which is the pi, which is supposed to be d pi. Yeah. And I'm going to put back the circle again so that we can create the square. And the square is created from 5 circles, like circles which are all connected one to the other, you know, just like that, snugly, so softly, so sweetly, like that. Yeah. And then we create the square right there. We can either keep the circles, and from what you can see out of the circles, you see the radius of each circle is 1.2720196, which is basically the square root of 5, the square root of the golden ratio. So if I were to redo the equation to the golden ratio, its square root is exactly what you see in that circle right there. And you see it 4 times. So we're going to remove these circles right here. We don't need them because what we need is the square. And like we said, if ever the equation was correct, then the square should have a length of, and I'm going to do it again, 1 plus the square root of 5 divided by 2, which is that, multiplied by 2 multiplied by pi, giving us that, divided by 8. It should give us that right here, which is right there. Yeah. So let's go back and check the square. The square is going to reveal to us exactly what it is. And so it's going to show us, it's supposed to show us that number multiplied by 2. Because of course, again, when I did the equation for that one, in order to reveal that number right here, I divided by 8, because I was thinking of the pyramid of Giza, you know, and the pyramid of Giza, they are not cut like in 4 as you would see, because there's some sort of an indentation on the slopes, making it look as if there's like 8 sides instead of 4, you know. But if ever you were to divide it by 4, then that would give us this exactly, you know. But that here that you're seeing, that's a mistake, because the number pi that we're using right now is wrong, you know. And if we go back to the square right there, it proves that the number pi is wrong, because it gives us the 2 times the, let me show you, because right now okay, it's not showing this properly. There. And if I do this, you see that it gives us exactly the square root of the golden ratio, you know? And so, check this out. Check this out. Now, you see like this here was supposed to be like, it's supposed to be that, but it's not that. But everyone says like that, okay, that pi is the correct pi because it's because of pi that it gives us that, you know? But it's not the correct pi, because if you do 4 divided by that number, it gives us a pi that is not the pi, you know? Because the pi that we're using is 3.1415926535459, you know? But throughout the whole of the equation, which we did again, also okay, what we got right there, and you see the pure simple equality in the way this is presented, you know? Even the slope of the triangle here is exactly the same as the length, as one length of the square, you know? And so if ever I was to take 4 divided by the square root of the golden ratio, so let me do the equation again, and I do the square root, so that's what it gives us again. And what that gives us is exactly what we see at the base of the pyramid right there. Okay? And so check this out. If I were to take the golden ratio as the radius, multiply by 2, and then multiply by that pi, it would give us 10.17615 whatever, you know? And if we check the parameter of that square right here, it shows that it's a parameter of 10.17615 something, you know? And let's not forget that all of this construction came directly from one circle, that same circle which you see like totally at the end of it, you know? And if I check the measurements, you know, right here, you see the circumference right there, and you see like the perimeter right there. They're so close, so close. I'm telling you, it's so close. Okay, it's nasty. It's nasty how close it is, you know? I mean, it came from the same circle, and it was constructed out of the same circle. If I check, like, let's say for example, the angle, I was saying okay, that the angle was 51.82, that's that's 72.92, you know, whatever. Well, there's no dot everywhere. Okay, I'm just playing with y'all. It's 51.827292.4 degrees, you know. But I doubt okay, that this is correct, because when that part, okay, I'm probably going to talk about that part some other time on the reel, because it's rather complicated, and it involves trigonometry, it involves sine and cosine and tangents and stuff like that. And I'm a little bit tired right now. That here, oh yeah, well, it was shown, it's already been shown. So the last thing that I wanted to show was that thing right here, where you take 1 plus the square root of 5 divided by 2 again, and then you do 1 divided by that, and you see that it does as if it's the square root, the golden ratio minus 1, You know, so golden ratio minus 1 and 1 divided by the golden ratio is exactly the same answer, you know? And that proves equality, but that's something like we can discuss some other time. Why I wanted to show you this is because if we take a line right here and we connect it here, and then we draw a circle right there. Yeah, I'm just gonna remove the line. We don't need that no more. Yeah, you're gonna see that the circle is exactly 1. That's deep. The circle has a radius of exactly 1. That's pretty much deep. So this means that if ever the radius of the very first circle was 1, the circle in the center would be that. That's intense. That's deep. And so if I remove all the lines, like the unnecessary lines, the lines which we don't need anymore, and we keep only what's necessary to look at right now, that's deep. Let me take away like that circle. That's the mystery circle. That's a circle that's not supposed to be there. But still, that's deep. You look at it like the construction is like, when you're looking at it, it's as if like it's alive. I don't know. It's alchemical. It's deep. You know. There was an understanding saying that let me show you something. That here doesn't prove that much. That proves just enough, but not as much as what I am going to show you in a few moments. That I'm just going to take a screenshot. So beautiful. But let me do another one. This one, I'm just gonna make sure that I make it large so that this way you can see exactly why I love the other pi as like the 3.1446 as opposed to that pi, the 3.141516 whatever, you know. Check this out. So let's go with the premise that we're taking a radius of 400. Okay, let's go with a radius of 400. No, let's not even do a radius of 400. We've seen what it does. It does a triangle. You know, it does a Kepler's right triangle. That's what it does, you know. So, and I know exactly which one gives that. So I'm just gonna do it right here. Just on a second. It's pretty much interesting too, so bear with me. That one, that's going to be pi multiplied by 100. There we go. Perfect. And I just need to find the golden ratio. Yes. First off, I just need to remove that. And right here on the slope itself, I will show the golden section right there. Now I'm gonna make the thickness like 1, like really thin. to draw a circle of that same type of thickness there. This here is pi multiplied by 100, and this here is 4 multiplied by 100. Okay, and connected to the golden ratio, look, I don't know, okay, I cannot draw anything right here, okay, but right there, okay, it's close to be so balanced, you know. It's like, it's crazy, you know. But if we look closely, we see that the circle is not balanced to the golden ratio. Now, if I were to change that pi here to the other pi, and there are many ways to find the other pi, I found a way, okay, that all I need to do is really just 320, like the square root of 320 minus 8, and then its square root, it gives me that. Bow. Just hold on a sec, I just did something. Let me just go back to 320 bow minus 8 square root bow. Oh yeah, I know now why a guy did something. I forgot to multiply by 100. Bow. There. Now that this is established, we know, okay, that this is still the golden ratio. It has not changed. Still the same position. We know, okay, that this is 4. That has not changed. Still the same position. And we know, okay, that this is a Kepler's triangle because the angle is 51.827292. That I know for a fact. That's why I knew exactly, okay, where to put that number and where to, you know. And I'm going to show you something after. It's beautiful. So with that pi, if we go there and we look and we look and we look, and yo, I'm telling you again, I'm trying as much as I can, okay, but yo, that's the maximum, okay, that it goes to. But as you can see, it's pretty much on point. Golden ratio connected directly with the pi, and that here, if I do the circle right there and I do that circle right, no, not the circle right here, sorry, just let me do a B back. I do a line, I do this and I do that, and I take away that one, and I create a square out of this. Now check this out. That square, I am going to make it thick so that in this way, when I'm going to do like the whole and I'm gonna lock it, okay, to make sure that I don't lose anything. Clack, 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 clack. I remove you. I remove you. Bow. I remove you. Bow. Okay, I got that right there. Okay, you see that, right? Okay, you see that. Check this out. I have not moved the triangle. So the triangle is exactly where it is. The circle, okay, I just created it out of that triangle, and the square was created out of that triangle. Okay? Now, I will create the square out of the circle. So I will change the color right there. Green. Okay? And that's the circle first. Second circle, bow. Just on a sec. I cannot make it I cannot make it smaller, unfortunately. So let's move on. Third circle right there. Then we create the line at the bottom, which connects to the center right there. And you see how snugly that line goes from first circle to square, circle second, square, circle first, then goes third circle. That's deep. That's deep. Let's move on. Then after that, okay, we have that circle right there. That circle is basically, you remember, okay, when I said, okay, that the radius of that circle was was 2. The reason why it was 2, okay, is because the square root of 5 minus 1 multiplied by 1 plus the square root of 5 divided by 2. That's basically it. So divided by 2, of course, because it's the radius. But you see exactly my point. And that's exactly what's happening right there with that circle at the bottom. Yeah? So I remove, okay, like the 2 other circles because I don't need them. And you see the proof right there, okay? If I do 4 multiplied by the square root minus 1, if I'm not mistaken, it should give me exactly, yep, multiplied by 100. Badao. And that's exactly what you got right there. Yeah. Then we remove last line right here. And you would think like that, okay, that when you're looking at the triangle, it doesn't fit. It's as if like, nah, it's not gonna match anything. Check this out. Now, I mean, check this out. I create the triangle, okay, and with the colors of the pyramids of Egypt, bear, and bear. It covers the other line. It covers the other line. What do you know? What do you know? Well, I do know that this fits. It fits like a glove. And remember, I used that pi right there, of course multiplied by 100. I could have used the other one, and we can try, and I'm pretty sure it's not going to fit. I'm pretty sure. Y'all want to try? Okay, let's do this. Yeah. If y'all have money, if y'all got money, man, y'all want to bet on that one? Y'all want to bet on that one? Really? Okay, yeah, let's do that. Let me remove, I'll remove that circle, I'll remove, no, I'll keep that line and that line. I will keep the square. No, I'll remove the square. I'll remove the square again because I will I will retransform the very first triangle so that in this way, okay, you will see exactly what I'm saying. This here I keep, this here I keep, this here I keep, okay? I can always put back that circle right here. But of course, oh yeah, that's exactly what I wanted to do. Starting with the triangle, I make a square out of that triangle. And this one again, I'm going to thin out. I'm going to thin out the line. I'm going to thin the lines of all the others right after, you know, but I'm going to thin out the line of that one first. And then I'm going to thin the lines of the other pie so that, yeah, you can see everything. So multiplied by 100. Bow. Okay. Now that one, as you might have noticed, the angle changed, became 51.85 3974. Okay, so what we're going to do now, we're going to create a square out of that one, and I'm gonna keep it thin, one, and I'm going to put it black, boom, so that in this way y'all can't say I'm cheating. Bow, bow. Okay, and remember, okay, when we calculated this on the calculator, the length, okay, was 1.270 something something for the pi that everyone calls transcendental, and lo and behold, yeah, no, that's not it. I forgot, okay, that this here, okay, is like, oh man, I forgot that that's multiplied by 4 everywhere. So let's forget that for a moment. I'll do something else. Yeah, what was I doing? That square. So that's square right there. And so we remove that, and no, we don't remove that. Keep that. Zip. Give me the other one. Hey. Okay, you are just going to disappear for a moment, and you goodbye, and you reappear. Perfect. Now that we got that, okay, we're going to redo the whole operation all over again. This time, circles, thin, pretty thin. 1, and then 2, the line that comes with it, and then the circle that comes after. Make these disappear, and that disappear, and that disappear, and then we do the triangle right here. Perfect. And now we remove that circle, and for the moment of truth, witness. Do you see that? Do you see that? I am going to put a circle right there. In red. And that dot right here is like a distance. How much is that distance? Okay. And that distance right here describes that the triangle in blue does not fit with the square. It does not fit with the, how can I say, with the blue line right here. Let me redo that again. I like the colors. I want to make sure that the colors are correct. Right there. See? Where the green circle is, that's where the line was supposed, that's where the triangle was supposed to fit. You know? That's where it was supposed to fit. But there's a distance between that and that and at the center. Man, I'm trying to get the center. It doesn't want to go to the center. Yeah. Just 1 second. Bear. I need to just. Okay, that was. You can't say that's max. Oh, that's max for real. Damn. Okay. Still, if I was to take off that triangle right here, yeah, and I was to input that triangle right here, yeah, that triangle which is right there, it fits snuggles directly on that point, you know, because it was made out of that circle. There's no problem with the circle, you know. The circle will always like be good. There won't be any problems with the circle. The problem is with the equation itself, the pi. You know, everyone's been using the wrong pi, you know. It's like if we're checking the measurements on that here with the angles right here, you know, here it shows that and that's for the triangle. You see where it says length? That here, it shows pi multiplied by 200. But that's not the pi that everyone is used to. It's the other pi. The 314 46 something, the 3.1446. That's that other pi. You know? And it shows many other characteristics. For example, the slope right there is the square root of the golden ratio in negative and minus. I mean, come on. And I mean, if I was to take, let's say, and we go back to the golden ratio, 1 plus the square root of 5 divided by 2, giving us the golden ratio. And then we get that, okay? I'm just going to split the screen just so that in this way, okay, y'all, you can see exactly what I'm seeing. I mean, you have got to see what I'm seeing, you know? No, that's okay, right there. All this construction right there, and if I put the man, it's not showing. I'm just going to, let me see if I can do that. Yes, I can. Yes, I can. Yes, you can. Yes, you can. Come on. Man, that's not what I wanted to do. And now it's doing something totally different. Let's go back. Did it show? It's not showing. Let me do it again. It is showing? Man. I was using the wrong one. But still. Black on black. But black snuggly. Okay, that's the yellow one, but I don't need the yellow one. I just need the black one and that one. So black one, that's the triangle, okay, that was made out of this. And the blue one, that's the pi one. You see? That's a long line, like a long margin, like a long error. Right now, again, I'm thinking about like all these calculations that NASA have been doing for a very long time and all the margin of errors again they've been having again. So, yeah, you have to ask yourself, were they using the correct pi? And funny thing, if I go on Wolfram Alpha, you know, and I look at it like for I'm gonna make it easy for myself. I get square root of the square root of the square root of 320 minus 8. The square root of the square root of 320 minus 8. Yeah, that's gonna be a new song. Trademark. You see, yo, that's easy. Comes out of nowhere. I don't need to do anything. Let me save that. I love it. More digit. More digit. More digit. More digit. More digit. More digits. Yo, looking for numbers of repetitions on all of these, you will find none. You will find none. And the thing is that when I'm looking at it, it's like reading a book. That's weird. Maybe again, I need to look at it again, like from afar again, but I don't know. It's like the numbers, they're like ordered in such a way, like the number ones, some of them on top of others. It's like, I don't know. Maybe it's the way it should be presented. Right now on Wolfram Alpha, the way it's presented, it's like that. But if ever it was a bit wider, I don't know. You know? And then we have that thing right here. The minimal polynomial, you know? Everyone says like that again. I don't, well, I'm not going to pretend that I know exactly like why this is important, but I did try it anyways, you know? And I did something like this. I did, what did I do? It was pi 4 plus 4 squared multiplied by pi squared, and then minus 4 squared, no, 4 like that, yeah, and 4 like that, that's 256, yeah. So this means that that first portion right there, the nat here plus that multiplied by that, supposed to be 256 too, but it gives us 255, hence the reason why 255 minus 256 equals that. Okay, so I tried to check with the other one. So the other one, for those who don't know the equation, you can do either 320, like the square root of 320 minus 8 and square root all of this, and it gives you that, or you can do 4 divided by the square root of 1 plus the square root, no, let me rephrase that, 4 divided by the square root of the golden ratio, just to make that simple. Wow. And it's exactly the same, exactly the same. Okay, so if I do the minimal polynomial equation right there, we're using that one for like the pi to the power of 4 with 4 squared multiplied by pi squared minus 4 to the power of 4, but now gives us 0. And I'm like, whoa, that's deep. What does that mean? What does that mean? Is it possible like that the minimum polynomial like it has something to do with, like, I don't know, 0 point? something. I don't know. Yo, somebody has got to explain this to me. Me, I'm trying to understand these mathematics, and the only thing I did not understand was pi way back in the day. So I spent most of my life trying to figure out pi, you know. And I think that we did figure it out. Like a whole lot of us, okay, did figure it out, but a whole lot of you don't want to use it. I don't know why, you know. And there was something else, okay, that I noticed out of that pi, you know. And I don't know. I mean, out of that pi, if I do, let me do this again. If I do this pi, I need to have like at least 3 parentheses, okay, on that one, okay, to do this. So I take that pi divided by 4, and you don't know that yet. That's basically like the square root of the square root of 1 over the golden ratio, you know. But let me go back to this. Divided by 4, it gives us that. Okay. Well, eventually I would need to do that in order to do the rest of it. So I do that, then that, and then I do that. It's deep. It's like it's magic, you know. And then after that, I do multiplied by 6 over 5, and it gives me another pi. And that other pi has some very interesting properties, because if you do divided by 6, it looks like the cubit in meters, but when you do the square root of that cubit in meters, it's like exactly like practically exactly the same, you know. But then also something else, if I were to take that multiplied by 10 minus 3, yes, minus 3, it gives us that. And if I do the square of it, it gives us that, which is pretty much intense coming out of that. And so I tried to do a few things with that one, but I don't know exactly which one is most important, you know, because both of them come directly from the golden ratio. You know, is it that one, or is it the other one, the one that we've been talking about? I say it's the other one, and the reason why I say it's the other one, check this out. If I were to take 4 divided by, oh yes, by the way, to get to the, just to get, oh snap, that's today, I forget that, that's not going to happen. So in order to get to that other pi, the equation is 3 over 5 multiplied by 3 plus the square root of 5, and that's what it gives us. Yeah. And so the reason why it gives us that is it's really just all in the square root of 5. It's all in the square root of 5, really. If I take the square root of 5, I just add 3 to it, divided by 10, multiply by 6, you got a pi. I mean, come on. And then out of that pi, okay, I multiply it by 5 over 6. It gives us the square of the golden ratio, goes back to the golden ratio, goes back to 1 over the golden ratio, goes back to the square of 1 over the golden ratio, multiplied by 4. What do you know? And then after that, if I take let's say 4 divided 4 squared divided by the traditional pi, which is that, and then I square it minus that pi, which is that. Normally it would give us 16, which it doesn't, but the other one does. The other one does. The other one does. How many scientists are looking at this right now? You know? How many scientists are looking at this right the F now? You know, it's supposed to change the world. I don't know how, but yo, before you can change the world, you have to change your mentality. And in order to change your mentality, you have to look deep within yourselves. Yo, I don't have a degree. I don't even go to university. Come on, man. What you talking about? And you know how you get to figure that? Yo, you go back. Check this out. If you find like a few things on Wikipedia, you like, check this out. Pyramid of Giza, the Great Pyramid of Giza. Okay. You know, in alchemy is a word that comes from alchem meaning I think it means the black land. That's what it means, the black land, alchem, you know, and that's where not alchemy, but that's where like everything that has to do with chemistry comes from, you know. So out of all this, there's something that's called squaring the circle, you know, and I mentioned this, I guess, a little bit earlier on, where it says like that, that in order to square a circle, the circle circumference has to be exactly the same as the square perimeter. And look at the pyramid. The base of the pyramid is a square, you know, and so if you take that square, take the perimeter and divide it by the height of that pyramid, it gives you pi. Or it's supposed to give you pi, you know, it's supposed to give you pi. I don't even know why, like, people, they've been like, yo, we're trying to figure out what pi is and all that, and we're going to get like after like the last infinite number, you know, but yo, you have to look this up. Where is it? I say you have to look this up again. There, it's right there. You see, it says the base 230.33 meters, and the height 146.6 meters. So let's take these numbers. The first one we said 230.33, and that's the length. That's the length of the base. It doesn't say like that, that it's the perimeter. That's the length of the base. That I'm pretty sure. I'm looking at it right now. It looks so much like the length of the base. Let me see. Let me do that just to be sure I'm saying this correctly. Multiplied by 4 divided by 1. Oh, I was so close. So close. Yet so far. Because it's supposed to be like that. God damn. Jude, wake up. What are you doing? Multiplied by 2. Divide. Yes, if the height is like that, then I have to see in like a sphere in a 3-dimensional way. So this means like that, that it needs to be divided by 2 times. 2 times but that does not make sense, because then I would have to multiply it by 4. So I was right all along. The base of it was the length. So if I do this like that, 230, which is the base perimeter of the pyramid, multiplied by, well, base perimeter, base length of the pyramid, multiplied by 4, which gives us the base perimeter, and then divided by 2 times the height, because the height is both looked up and down, as above so below. Badao. It makes sense now. As above so below. It was all related directly to the pyramids and the squaring of the circle. Oh! But yeah, this one is so close to the Egyptian by that one. But, you know, we have to consider the pyramid, the perimeter, which is a square, which is 4, you know. And if we take that, you see that what it gives us, minus that, and that's what it gives us. The reason why it's like this is because if you take, let's say, 16 divided by pi, it gives us that, right? And if I do like that, the square of that minus the square of that, it gives us 16. And eventually, of course, if I take pi multiply by that, so it gives us 16, right? But that's not the case with that pi, you know. If I do that divided by that pi right here, it gives us that. So if I do the square of that Pythagorean, you know, and I take that right here, it gives us 16, right? It gives us 16. And eventually, of course, if I were to take that multiplied by that, it gives us 16. What are we looking at right now? What are we looking at? Huh? What is it that we're looking at? Why is it that we're using that other pi, the 3.1415 whatever? Don't come and don't brutalize me. You have got to accept that. You need to advance in life, man. Come on, what y'all doing? On the real. Yo, check this out. It's too beautiful to kill a pie. It's too beautiful of a pie. Hey, check this out, okay? If I do, let's say, for example, if I do this, 4 multiplied by the square root of phi, which gives us that, multiplied by 2, multiplied by 4, divided by the square root of phi, which gives us that, it's going to give us a circumference of 32. 32. And the way it was done is because it's, let me show it like this, is because it's 4 multiplied by the square root of phi times 2 times 4 divided by the square root of phi. Yeah. There is balance and magic and science in the golden ratio, hence the reason why it's called the golden ratio. The golden ratio is practically the father of pi. Yeah, and the only reason it's like that is because of square roots, man. It's deep. I love square roots. Although again, I don't know how to calculate them well on like traditionally speaking. Like I said, I'm not really that good in mathematics, you know. I love the calculator though, and if my teachers again had taught me again like correctly again, I would have been a great scientist, I guess. I don't know, but y'all, I'm relegated to using a calculator just to make sure that I know exactly what I'm doing. But even the calculator, I cannot trust. I cannot trust the calculator. Because on the calculator itself, if let's say for example, I go okay with the angles, in degrees, and I said like that okay that if ever okay this was the correct degree, then basically okay like the real number would be that, and the imaginary number, lo and behold, is that. What do you know? What do you? What do you know? What do you know? Oh, what do you know? I figured out something else, but I'm not sure if this is correct. I hope it is, but it involves 21 over 25 multiplied by 1 plus the square root of 5, and it gives us that. I'm pretty sure some of you know what this looks like. If not, you can check this one out. But what's interesting about that one? What's interesting about that one? Well, let's check it out. What's going on? What's going on? Multiplied by the golden ratio, multiplied by 5, divided by 7. What? Is it really? Exactly the same. Exactly the same. And we all know okay where this one comes from. We can do it again. Let's try it again. Yeah. We take that one multiplied by 5 over 6, and then it gives us. Okay, no, I'm not good with the music anyways, man. But still, you see what it gives us. And then we go back, and then we go back, and then we go back, multiplied by 4. Yeah. And then we know the proof already. We already know the proof. We know the proof, right? We know the proof. At 12 precision. At 12 precision. At 12 precision. At 12 precision. And that thing here does not have like any, there's no way possible for it to be associated with any kind of repetition in the decimals. I mean, I could do like 91 over 8 do equal, and then press that button several times again. You'll see there's repetition in the decimal. Repetition in the decimal. I can take that one right there, try to do the repetition in the decimal. It does not exist. It does not happen. It never happens. I don't know why. But that's more or less my presentation on the real pi. The real pi is 3.1446. It's been said more than once, and I'm pretty sure that once you're going to rewind it again, you're going to see the part where you see the slope in the golden ratio and the circle that connects to that golden ratio, and then you see the line that doesn't fit, with pi. Then you're going to be like, oh man, what have we been doing, man? Maybe we've been messing up a few things, like with our spaceships and our orbit, and also with the galaxies and whatever, man. Maybe we'll be able to understand time a little bit better, I mean, come on, man. Yeah, this comes from the backwaters, man. Come on, do something. Yeah, already with the life that we're living right now, man. Life is hard, man. Life is hard, So, I mean, use the knowledge if you want, if you can. If you can't, well, that's you. If you can, well, good for you. And me, I'm too old, and I can't build anything. I just talk. I just talk now. That's all I do. I talk. There's too many people out there nowadays that all they do is just talk about things that really don't matter. We'll talk about things that matter. Things that do matter, like food, shelter, clothing, stuff like that. Helping your friends, Stop killing people, start educating yourself. I mean, start becoming one. Stop populating, like pushing babies, like left and right, up and down. Like, yeah, this planet is not a whorehouse. Yeah, you're born, like to learn many new things, like to like you're in a cocoon, you know. You're like in a cocoon, and I'm trying to figure out. You're like in a cocoon, and you have to find like a way to break out of that cocoon. You know what I'm saying? Because if you don't break out of that cocoon, you're gonna make mistakes, much like that mistake right there with that pie right there. Okay, that doesn't fit. You see, it's a pie that does not fit with an angle of 51.85, that 30 something, If we remove that one, okay, I don't know if that's the one. Yeah, that's the one. That one, okay, is like it's pissing me off every time I'm looking at it, And we go with the yellow line right there, okay, which fits. It's snuggled. It's snuggled. Snuggled. And then after that, if ever I was to take like just to so that okay, you can see it clearly this time, okay, I'm just gonna make it thick, like real thick. And you take that right here, and you check the numbers. Here we already know, okay, it's a 400, but I've removed the other one, so the triangle now fits correctly on both the square and the circle. And of course the pi, which is shown as 314.46 for this instance, because it's multiplied by 100, but it's 3.144605511, and it will never change. Just to be certain that you understand clearly what I'm saying, let me do this one more time. And this time, what I'm going to show you, it is going to blow your minds. It is going to blow your mind. If you've never had your mind blown, well, be prepared. Be prepared. And anybody, okay, that wants to hurt me because of that knowledge, okay, that's your loss on the real. You will go back 800 years back into the Stone Age, like into the Dark Age, if ever you decide to do anything onto me or anybody else. Trust on that. Because stupidity, ignorance, okay, like that leads really to what Yoda said. Like in Star Wars, you remember in Star Wars what Yoda said? If you fear, it will lead to anger, it will lead to this and that and that. Why? Because you're ignorant, and it's ignorance that leads to all that. You should watch Star Wars, George Lucas, kudos, man. You did a good thing. That's a beautiful thing. Trust on that. I shouldn't like name like that, man. Trust. I'm going to edit that thing. Snap, man. That's going to hurt me after that, man. I hope you too, okay, is going to give me something good. And anyways, let me show you, okay, what I wanted to show you. And if ever this is really good, I hope, okay, this is going to pay, okay, for anything, okay, that I'm saying right now. But one thing I'm saying, okay, never, ever, ever, like, use the truth as a, like, for commerce and thing, The truth, okay, is really something beautiful once you come to understand it. So I create one more circle, that one with a thickness like that, so that in this way we can see exactly what we're doing. That is wrong. That is wrong. And we're going to prove it. This time, okay, if we're going to prove it, we're going to prove it two ways. We're going to start with that one first, and we're going to retrieve the square from that one to see what the circumference of the square is. You see the circumference of this one here, what it is? Remember that. Remember that. Okay? We're going to do it the same way, okay, that we've been doing it like since the very beginning. You know? The Samuel Leboy formula, also known as the perfect symbol. You can look it up. Samuel Leboy from Puerto Rico, engineer. Yo, this guy, okay, is a genius, man. He is a genius. I've never ever found anything so genuine as that. That is genius. Check this out. So we're going back to the formula again, and it's a pretty simple formula, really. All you need to do is really just like you do 3 circles, like interlaced one into the other, you know, and then afterwards, okay, you connect them with one line from the bottom of the first circle to the center of the third circle, and then you create a 4th circle which connects from the bottom of the first circle to the edge of the 3rd circle, you know what I'm saying? And then once that is done, you can get rid of the 2 other circles and even the line if you want to, and from there you can create like a triangle. From here, because I'm using geometry pad, you won't be able to see it like full length. I wish I had like another one. I could use another one, but I'm using that one because this one again is it's marvelous. And so I just did the triangle. I removed that circle. I don't need that. And just to show you that it is possible to do it with a square and compass, I'm doing the circles right there because afterwards you need to have a square, and in order for you to have the square you need to have the circles, and that's how the square is born. The circle is the father of the square. Check this out. Well, I said the father of the square, but the circle is like, it's round like a woman, so I would say that the circle is the womb and the mother of the square. It makes more sense, you know, because and the triangle in the very center, again, I guess it's like the fire within that creates both, you know, like the unity between the circle and the square. You know, that's the way I see it. I don't know. It's really just speculation. Don't go with what I'm saying. You know, that's my own opinion. Maybe it's something else. I don't know. One thing I do know, it's beautiful to look at. It is. Yeah, check this out. So I do that, and then I do that again, and then I remove that here. Perfect. Now that this is done, before I get that phone call, I'm just going to create that right there. I do 2 things. The first thing is I'm going to create a square. Well, no, I'm going to create several squares. First off, I'm going to create the triangle first, all in black right there. Okay, and I'm going to change its thickness just a little bit, so that it demarks itself, you know. And then I'm going to start creating those squares. Yo, the squares, they're beautiful. I'm going to do that one right here. Let me do it again. It's because it's too small. Right here, right there. Okay. Now let's remove the circle, the lines, and let's keep which square did I put? Okay, let's remove the first square, let's remove the first triangle, and we keep that exactly what we want. Perfect. Now right here we have number 1. Okay, and let me remove that one for a second there. At the bottom, what am I doing? I don't need to remove that. Stay here. At the bottom we have You've seen that before, right? I know you've seen that before. Let me bring you that square once more. Yeah? You see that square, right? I'm pretty sure you do. And so that square, if we go into the metrics right here, we do remember, okay, what the pi looked like on the other one. Does it look like that one? Did it look like that one? Let's see. We're still using the old pi, right? Okay, so multiplied by 2. That's the pi, okay, which we're looking at. And here, okay, it's how many numbers? 1, 2, 3, 4, 5, 6. Let's go for a 6 right there. Wow. Okay, so 28, 31, 85. That's what we would normally see on the circle right here. And just to show, okay, what I'm saying, you know, let's go. You see? But you see the parameter at the bottom where it says quadrilateral, right? That one, okay, if you recognize what that one is, yeah. Let me go back, okay, to the first square right there. Do you see the parameter right there? Do you see where it come from? Do you see where it came from? Do you see where it came from? Do you see where it came from? It came from the circle. There's a circle radius of 1, revealing a square with a perimeter of 3.1446055, exactly the same as what we've been calculated since the very beginning. Now, there's something that I've uncovered on Wikipedia, and that's funny. You know, that's funny. I found it like very, very funny. You know, mathematical constants. Coincidences, not constant. Coincidences, yes, that's the one. Yeah. And in mathematical coincidences concerning pi, okay, right there, a coincidence involving pi and the golden ratio is given by pi equal 4 divided by the square root of the golden ratio equals 3.1446. Consequently, the square on the middle sized edge of a Kepler's triangle is similar to the perimeter to its circumcircle. Some believe one or the other of these coincidences is to be found in the Great Pyramid of Giza, but it is highly improbable that this was intentional. I mean, come on. That shows how little we think of ourselves. Yo, but check this out. Okay? I don't know yet. I have to discuss that portion again, like with mathematicians or something like that, you know, about the qubit on that one and the qubit for the other one, which is the one again which stems from the first one, which I'm showing right now, you know. So let me show you the qubit of that one. Okay, so here's something. Okay, if I do that multiplied by 6 equals that, and if I do 12 divided by that, oh no, not that. If I do 12 divided by that, and then 1 over that multiplied by 10, Tao. That's weird, okay, that it does that with that qubit, you know, especially the fact, okay, that qubit itself, okay, is gives us that already right here, okay, which is pretty much messed up in my mind right now, you know. It's like it's exactly the same. The square root of that qubit gives that, and it's exactly the same. It's messed up. I could multiply this by 10 and then do minus 2 and then divide it by 10 and then redo the same process all over again. It's a funny thing. It's really funny, you know. But this one, like, it doesn't seem to have like any other properties aside from that. I don't know. Maybe it like scientists, like, he can figure out something. The other one on the other end, since, okay, of course, it comes from the true pi. When I do, let me see if that works, because I was doing that, and I was doing that, if I do remember, and then I was multiplying that by that. Yo, man, that's like, yo. But I mean, I don't know. If ever I was to do it like that, divided by that here, but we came with the conclusion that that here was the correct one, then doing what we just did a few moments ago would have given us 30, when instead it gives us that multiplied by 10. It's pretty much close to the light speed. It's confusing, I know, it is confusing, but I think that the light speed itself has something to do with the qubit as well. Maybe it wasn't supposed to be 299 something, maybe it was supposed to be 300,000 after all. Who knows? But there are some of the things that were being explained by some more knowledgeable people, stating that the height of the pyramid, for example, initially was greater than that. So this means that it wasn't 146. It might have been maybe 6 meters greater than that. Who knows? In anyways, man, I'm tired and I'm hungry. So, and I'm not being paid, okay, for doing this, okay. So I'm just going back home. Alright, just going back home. I'm already home. I'm just going to sleep. Alright, talk to y'all later. And if ever you want to leave a message or anything, you don't hesitate. Don't hesitate. Me, what I do, generally, I'm on Twitch playing Call of Duty and some other video games. So check me out. Peace.